So we'll continue to the last talk of the day by Paolo Gregori on Resurgent ZZ and FZZT branes in minimal strings, Jackiw-gravity.
Thank you. So good afternoon, everyone. Well, let me start by thanking the organizers for inviting me to give this talk, and thank every one of you for being here to listen. So since it's the last talk of the day and we're all tired, I will try to keep it simple and make several long stories quite short. This is, I will talk about a... Yeah, okay. So I will talk about a project that is ongoing with Riccardo Schiappa, and that was later joined by Bertrand Einar, Elba Garcia-Failde, and Danilo Levansky. And it's a project that started as with the aim of sort of classifying and computing non-perturbative effects in a set of two-dimensional gravitational theories. And well, the idea was also to try and see if through these non-perturbative effects we can reproduce some behaviors in a specific set of observables that we know show non-perturbative physics in them. We started by considering a large class of models, minimal strings and JT-gravity, also multi-critical models. And these models are particularly easy to study in a sense because there is an underlying matrix model description. So we can use tools like topological recursion and other techniques by resurgence that were already established in the literature to study these kind of models. So let me tell you, first of all, what is JT-gravity, which will be the main character of this talk, even though as I said, we dealt with a wider class of models. JT-gravity is a model of two-dimensional dilaton gravity with the action that I wrote here, which is comprised of a topological term and then an action for the dilaton field, in which you see that the dilaton enters just as a Lagrange multiplier. So what it does when we perform the path integral is just enforcing a negative constant curvature of the space-time. Bear in mind that we will not use this kind of formulation of the model. As soon as I will introduce the matrix model dual, we will just work with the matrix model. The topological term is such that whenever we perform the path integral over a space-time, essentially every contribution to the path integral is weighted by e to the s0, which is this constant here that appears at the beginning of the action, to a power of the Euler characteristic of the space-time we are integrating over. So observables essentially organize themselves naturally as topological expansions. And as you might predict, all these topological expansions will be divergent and we will have to make sense of them somehow. And this is a story that is already, people who are familiar with matrix models, this is a story that they have seen many times. The interest for this model came because it was found to be the holographic dual of the SYK model, which in turn had attracted a lot of interest because of its properties, holographic properties. And the connection with random matrices was suggested very early on, but it was made precise only quite recently. So the kind of quantities we want to study are the so-called Euclidean partition functions, which are expectation values. They are obtained by performing the path integral with the action that I showed you before over space-times with M boundaries and G handles, right? And it was found by Schenker and Stanford, but I think the original suggestion was by Witten, that essentially these kind of observables are encoded by Weil-Petersson volumes. So I don't know if you know what Weil-Petersson volumes are, but you can think of them as arising by integrating some special classes on the moduli space of curves. It's not important what they are. What is important is it's been known for a long time by the works of Mirzakhani, Zograff, and others that these objects grow factorially like 2G factorial. So we expect resurgence to be at play somehow in the computation of these observables. Now, an Euclidean partition function that we are particularly interested in computing is called the spectral form factor. It is a two-boundary Euclidean partition function where the variables are set to be beta plus it and beta minus it. The importance of this object is not easy to explain in a very short time, but let's say that it is taught in systems that are related to black holes and which satisfy certain notions of quantum chaos, which were introduced by Polchinski and others. It is thought to have a universal shape, which corresponds to this initial dip, a slope, and then a plateau. And this that I draw is the exact form for this object for the area example that I will tell you later what this area example is. You can consider it a toy model of which the JT gravity is a very non-trivial deformation. The idea is that if we just use perturbative data to compute this object, we never see the plateau. So the plateau needs to be captured by some non-perturbative contribution, but it's non-perturbative in a subtle sense that I will make clearer towards the end of the talk. Now, let me briefly outline what I will talk about. First, I will give you a very lightning review of matrix models, just to set the notations essentially, and to show you what kind of matrix models describe this set of 2D gravitational theories. Then I will classify the kind of non-perturbative effects that appear in these matrix models, and I will show you how to compute them using topological recursion. Then I will introduce the very basic tools from Resurgence that we will use to to study the interplay between these different non-perturbative effects. And then I will show you how these non-perturbative effects manifest themselves in the form of singularities in the Borel plane, as you all know, and also they show up in the large order behavior of the perturbative series. Finally, I will show you how these non-perturbative effects affect a couple of observables that are of particular interest for us. And I will then conclude with a summary of the talk and some open ideas. Now, regarding matrix models, Max, for example, has already told you a lot about them, so I don't have to tell you much. Just to fix the notation, I call a matrix model a model that whose partition function is given by an integral over matrices with some potential v. And I'm considering n by n Hermitian matrix models. Now, the usual lore is that in the large n limit, one can associate a spectral curve to a matrix model whose shape in the one cut case is of this form. So you have a finite cut running from A to B, and then some function m of x multiplying the cut. Now, the idea, if you want to visualize where this spectral curve comes from, you can see it as the derivative of the effective potential acting on the eigenvalues. So in the large n limit, the effective potential typically takes the shape of a flat interval corresponding to the cut, which is where all the eigenvalues perturbatively want to sit. And then outside of the cut, it will have some behavior which will include non-perturbative saddles, so minima and maxima. The spectral curve is also related by a very, very simple relation to the spectral density of eigenvalues. So the eigenvalues, as I said, perturbatively want to sit on the cut. So the cut of the spectral curve corresponds to the support of the spectral density of eigenvalues. Now, in matrix models, a very standard quantity we want to compute are correlators of resolvents, which take this form. They are particularly useful because they essentially act as generating functions of all multitrace correlators of matrices. So this is the basic object we want to consider. They depend, the endpoint correlator, of course, depends on n variables, zi. And of course, they have a perturbative expansion, which also in matrix models organizes itself as a topological expansion, because you can always see the Feynman diagrams of matrix models organizing themselves according to the topology of the surface on which you can draw them. And these objects here, the coefficients of these expansions, which are, by the way, formal power series in the sense that these coefficients grow factorially, and so we need to resum them somehow. These coefficients WGN can be computed recursively using topological recursion. Now, I don't want to go into the details of what topological recursion is. You can see it as a machine that spits out for you these WGNs when you know the WGNs with lower Euler characteristic. So it has a kernel which depends on the spectral curve. So you can say that the spectral curve is the input that you give to topological recursion, and then you run the you run the machinery and you compute recursively all the WGNs. Now, it's not completely true that the spectral curve is the only input you have to give topological recursion. You also have to give the W02 coefficient, which typically for matrix model has a uniform, universal shape. So it's always the same W02 for all matrix models, at least in the one-cut case. Now, how do we obtain the matrix model that describes JT gravity? This was done by Saad, Schenker, Stanford, and Witten by essentially computing the JT path integral on the disk topology and extracting from it the spectral density of JT gravity, which was then conjectured to be the spectral density of some matrix model. And from the relation I showed you before between spectral density and spectral curve, we can extract the spectral curve of this matrix model. You will see that it looks a bit different from the spectral curve that I showed you before with a finite cut going from A to B. This is an infinite cut spectral curve running from -infinity to 0. And you can see it as a double scaled matrix model. So I don't want to get into the details of what the double scaling limit of matrix models is, but you can picture it as a particular way of scaling the parameters of the matrix models in such a way that you zoom into one of the endpoints of the spectral curve. So the other endpoint runs away to infinity, and you're left only with an endpoint at the origin. In this particular case, the JT matrix model, the WGNs, the VGNs, which were the Weil-Petersson volumes, and the ZGNs, which were the coefficients of the perturbative expansion of Euclidean partition functions, are all related by a web of integral transforms. Very roughly, you can say that the VGNs are the Laplace transform of the WGNs, and that the ZGNs are the inverse Laplace transform of the WGNs. Now, this is not all we did, in the sense that instead we actually started from another class of spectral curves, which are the spectral curves of 2, to k-1 minimal strings, which in the k to infinity limit, if we take it in a particularly careful way, give you the JT spectral curve. So what are minimal strings? Also, it's not going to be very important what their worldsheet theory is, but you can see them as a Liouville model coupled to some conformal matter in the form of a 2, to k-1 minimal model.
Sorry, just a terminology.
Yeah.
What is the spectral curve of the JT gravity? Is the spectral curve of the boundary related matrix model?
Yeah, you can. So I think in these cases, rather than seeing it as a boundary theory, the matrix model is an alternative description. So it's a very long story, the interplay between 2D gravity and matrix models, because you can always see the matrix model as a way of the way the Feynman diagrams organize themselves in such a way that they are weighted by the Euler characteristic of the surface on which you draw them. In the large N limit, you can see the Feynman diagrams of matrix models as a tessellation of a two-dimensional surface. And it's in this sense that you should see the relationship between 2D gravities and matrix models rather than a boundary theory. So the boundary theory of JT gravity is the SYK model. The matrix model is an alternative description of JT gravity, which is not in a holographic sense, I would say.
Yeah, sorry, no, you're right, but no,
Yeah.
I meant the spectral curve in JT gravity. This terminology is still.
Yeah. So the spectral curve. So as I said,
disk amplitude essentially.
Yeah, it's the disk amplitude. Well, from the disk amplitude you obtain the spectral density, and from the spectral density you obtain the spectral curve. Yeah. And you can do the same with minimal strings. So the story of the relationship between minimal strings and certain double-scaled matrix model is a long story. And it has been known for a long time that they have this kind of spectral curve, which is given by a Chebyshev polynomial of degree 2k minus 1. And they essentially constitute a hierarchy of models that one can study and that we did study. The first few examples are the Airy curve, which is the simplest one you can imagine. And then, for example, already the second example is the Pain-Levé curve. Pain-Levé in the sense that the free energy, if you compute the free energies from this spectral curve, and then you compute the specific heat from those free energies, the specific heat satisfies the Pain-Levé string equation. So what kind of non-perturbative effects do we expect in these kind of matrix models? Max already showed you a kind of non-perturbative effect, which is perhaps the most intuitive kind you can imagine, which is eigenvalue tunneling effects. So the idea, as I said, that you have an effective potential which is flat on the cut, and it will have some other saddles outside of the cut. For example, I drew here one at x0, which is where the spectral curve is 0, because it's the spectral curve is a derivative of the effective potential. And what I call ZZ branes, which is terminology borrowed by minimal strings, so it's nothing scary. It's just an eigenvalue tunneling effect in which we let n-1 eigenvalues sit on the perturbative cut, and we just place one eigenvalue on the non-perturbative saddle. So as I said, Max already gave you many details about this kind of contributions. We will be much more humble and just study for one saddle the one instanton configuration, which takes this form that has been known for a long time. You see immediately that this is a non-perturbative contribution because you have this exponential of -a/gs. And then there is a perturbative series attached to it, of course, as usual. Now, the very nice thing about this story is that all the non-perturbative data that is contained in this equation, so instanton action and all the coefficients around this one instanton configuration, are captured by the spectral geometry, in the sense that, in some sense, if I give you the spectral curve, I can compute all this data using some form of topological recursion. Well, the very basic example is the instanton action that I can compute essentially by computing the difference between the potential at the non-trivial saddle and the potential at the cut, at the endpoint of the cut. And this is just an integral of the spectral curve. And in the case of 2,2k minus 1 minimal strings, we have the order 2k minus 1 Chebyshev polynomial, which has k minus 1 saddle zeros. And therefore, we have k minus 1 non-trivial saddles. And we were able to compute, well, actually, this was already in the literature, but we can reproduce this number here just by using this formula with the spectral curve. And this is the instanton action for the nth saddle in the 2k minus 1 minimal string. But this is not the full story. And also, this is something that, sorry, yeah. X naught is sorry, in the previous picture, X naught was the position of the saddle. This is not the full story. And well, essentially, Max gave a whole talk about this. It can be seen also from string equation considerations that there is actually a doubling of instanton actions in this kind of models. And this is where resonance comes into play. And in fact, we showed in a very general way that all these models feature this kind of resonance. Now, the case of JT gravity is much more involved in the sense that, as I said, you can see it as some k to infinity limit of minimal strings, and therefore it will have an infinite array of saddles with alternating signs. And the interesting part is also that every saddle is a multiple of the first one. So the first one, which we can call the unit instanton action, is 1/4 pi squared. Oh, yeah. And all the others are multiples. Yeah, in fact, here there's a typo, and there should be also an L multiplying everything. So for this reason, we expect the trans-series structure to be very involved, and we expect resonance to play a huge role in this trans-series. But we will refrain from trying to construct the whole trans-series. In fact, for our purposes, we will be very humble. We will just stick to one instanton contributions to everything we will consider. Now, the remaining data, because here I showed you only the instanton action, but the remaining data is computed doing a saddle point integral, passing from the non-trivial saddle that we are considering. And the function that we are integrating, that I called psi of x, is constructed by topological recursion. So this is a very nice way of packaging all non-perturbative contributions. We just have the WGNs that we computed through topological recursion, which are a priori perturbative coefficients. And by packaging them in this way, every one of them is integrating n times from -z to z. We construct a function psi that then constructs for us the non-perturbative data. This might seem a bit like, like it fell from the sky. Unfortunately, I don't have the time to explain in detail why this is the correct function to integrate. But for those who are interested, of course, I'm available to talk as much as you want. With this technique, we are able to, for example, compute the one loop around one instanton for all 2,2k minus 1 minimal strings and for all saddles. So n, as usual, labels the non-perturbative saddle we are considering. But we can do much more, actually, because the saddle point integral is something you can throw in Mathematica and let Mathematica compute for you. And so for the JT case, we got many loops around the one instanton configuration. Here I show you the first 5, but we got up to 12. Unfortunately, topological recursion is not a very fast recursion. So we cannot really go to astronomically high numbers, but still, it's funny that for us, computing perturbative and computing non-perturbative is essentially the same level of difficulty. Now, a very nice thing about this topological recursion technique is that it gives us for free, which is something that was not available before, non-perturbative data of correlators. Because in topological recursion, we have this operator called the loop insertion operator, which unfortunately looks a lot like an alien derivative, but it's not. I will not be using alien derivatives in this talk, so there will be no confusion. But it's essentially an operator, which unfortunately I cannot define precisely, but I can, of course, tell you later if you're interested. It's an operator that sends the nth at the endpoint correlator to the n+1 correlator. So, for example, by acting on the expression that I had before for the one instanton contribution to the free energy with the loop insertion operator, we obtain iteratively all the one instanton contributions to endpoint correlators. And of course, again, we were able to run this machinery algorithmically. And for example, here I give just this formula for the one loop around one instanton, which is, by the way, a universal formula because it involves only that WZ2 that I told you earlier is the same for all one-cut matrix models. So this is a rather neat fact of life that the one loop around one instanton takes the same form for all one-cut matrix models. Of course, we were able to run this machinery for many more loops, and we tested everything we computed. But here I want to show you only this one. Then, so far I showed you ZZ branes, that is eigenvalue tunneling in matrix models. But there is another non-perturbative effect, which might be a bit less intuitive to visualize in matrix models, and that you have not seen in Max's talk because it does not appear in free energies, but it appears only in correlators, which are so-called FZZT branes. And a way of picturing them is by picturing them as insertions of the determinant operator, so determinant of x minus m, or if you want, orthogonal polynomials. So the building block of this kind of non-perturbative effects is this function capital psi, which should not be confused with the lowercase psi I used before to compute ZZ brane contributions. And as you can see, the kind of non-perturbative contribution here is quite different because it is you have the exponential of minus the effective potential evaluated at x over gs. So now the instanton action depends on some variable x. And this is a striking difference with respect to ZZ branes, which had a constant instanton action. And we will see that this plays a huge role in the interplay between these two kinds of non-perturbative effects. So as I said, they contribute only to correlators. And in fact, for example, the W1 correlator, which depends on some variable Z1, will have a Z1 dependent instanton action. And also this contribution can be captured by topological recursion by a smart packaging of the WGNs computed by topological recursion. But again, this might look very similar to the lowercase psi that I defined earlier, but here the contour of integration of the YGN changes. And this is a crucial difference that makes these two objects very different from each other. Now, just to see how these two non-perturbative effects compete with each other in the observables we consider, let me remind you, well, actually, let me give you a very brief overview of the tools, of the very simple tools by Resurgence we will use. As I said, we are being humble in the sense that we do not aim to construct a realistic trans-series for the full observable we are considering. We just want to point out that to a given observable, we will have a perturbative contribution, some ZZ brane contribution, and some FZZT brane contributions. And typically, we will stop at the one instanton level in both. Actually, let me point out that there is another striking difference between ZZ branes and FZZT brane contributions, which is in ZZ branes, you typically have the standard tower of singularities in the Borel plane. So you have multi-instanton sectors associated to ZZ branes. For FZZT branes, instead only produce a couple of singularities in the Borel plane. In the sense, a couple because you always have the plus and plus minus a. But they do not produce this tower of singularities. Now, of course, when we write something like this and we stop at the one instanton sector, we are missing multi-instanton contributions and resonance, which, as I told you, is very general in these models. But for our purposes of understanding some non-perturbative effects in a certain class of observables, and also for checking the large genus asymptotics of the perturbative sector, this is enough. Now, what kind of Borel plane singularities do we expect? As I said, we expect constant singularities associated to ZZ brane singularities, which are this blue square. Of course, I'm drawing just a quarter of the complex plane, so we miss the pair with the opposite sign. And we expect FZZT brane singularities which move around in the Borel plane as we change the variable x. Another tool that we will be using, and that I'm sure most of you have seen before, is resurgent large order relations, which I will very often call large genus asymptotics. Genus because, as I said, our expansions are topological expansions, so they are expansions in the genus of the surface. And we all know that singularities in the Borel planes are attached to non-perturbative sectors, and by a smart application of Cauchy's theorem in the Borel plane, we get a relation for the large order of the coefficients of the perturbative sector in terms of all the non-perturbative data associated to the other non-perturbative sectors. Here I wrote just 2 lines of large genus asymptotics, and you can picture it as, you know, contributions from just 2 singularities in the Borel plane, and you see that we see immediately the expected factorial growth embodied in these gamma functions. Of course, both sectors will have some characteristic exponent which appears here, which I call beta. Then we see an exponential growth dictated by the instanton action, which is the position of the singularity in the Borel plane, and then a set of subleading in powers of 1/g contributions, which contain all the coefficients of the non-perturbative sector that we are considering. So you see immediately that if you have only 2 singularities, for example, the singularity that will dominate the large genus asymptotics is the singularity that is closest to the origin of the Borel plane, and this is caused by this denominator here. Now, why are these large genus asymptotics particularly useful? Well, for 2 reasons. One way is to generate many perturbative coefficients through some algorithm, and then use these large genus asymptotics to check the non-perturbative data that we computed. Another way is because it provides us for large genus asymptotics of objects that might be of interest. For example, the Weil-Petersson volumes that I mentioned earlier. People who work in algebraic geometry or enumerative geometry, they are very interested in these objects, and they are very interested in their large genus asymptotics, which typically are very hard to compute. And I will try to convince you that the resurgence is a very efficient way of computing large genus asymptotics for objects of this kind. Now to the meat of the story, which is what are the actual Borel singularities? Can we actually see these Borel singularities appear in the Borel plane? Now, it's not easy to capture Borel plane singularities when you don't have a closed form of the Borel transform of whatever object you're considering. But we have essentially 2 ways of obtaining approximate Borel transforms. One way is to consider the matrix integral which encodes the observable we are trying to compute. So, for example, for the 1-point correlator, we have a matrix integral that once we have integrated away the first n-1 eigenvalues, we are left only with the integral over the last remaining eigenvalue, which takes this form. Of course, this is not the full story. We have truncated to the leading order in GS. But this is enough through a change of variables to obtain a so-called approximate Borel transform, which already encodes the singularities we expected. So in blue, we have a term that is singular when the effective potential is at a minimum or a maximum. And this is the ZZ brane singularity. In the second term, we have a singularity at the effective potential evaluated at x. And that is the FZZT brane singularity. So even if we had done some very brute truncation of the object we were integrating, this approximate Borel transform already captures the Borel singularities we are expecting. But if you're not convinced by this approximation, there is another way of doing this, which is through Padé approximants. So you generate some perturbative numbers with your favorite algorithm, you Borel transform them, and then you Padé approximate this Borel transform. The singularities of the Borel of the Padé approximant tend to condense close to actual singularities in the Borel plane, and this shows up in these plots that will take me a couple of minutes to explain because there's a lot of stuff going on here. We have the blue squares, which are the singularities associated to ZZ branes. So they are constant and fixed at some point on the real axis. Then we have the red circle, which is the singularity associated to FZZT branes, which will move around as we change the Z parameter. And then we have these six black dots, which are the singularities coming from the Padé approximant of the Borel transform. So as you can see, we started from a value of Z at which the FZZT singularity is closer to the origin, is inside this blue radius. So it's closer to the origin with respect to the ZZ brane singularity. And as you can see, this is reflected by the fact that the Padé approximant poles condense close to the FZZT brane singularities. But now we want to make the FZZT brane singularity describe this red trajectory by changing the value of Z. And as soon as the FZZT singularity becomes farther from the origin than the ZZ singularity, you see that the Borel-Padé poles condense to the ZZ singularity. Even if now it might seem that the FZZT singularity came back into the blue radius, you have to picture this as the FZZT singularity leaving the principal sheet of the Borel plane. So even if it looks closer to the origin, it belongs to another sheet. The Borel-Padé singularities still remain condensed close to the ZZ brane singularities. And of course, for the two-point function, you find a very similar story. But here we see two distinct FZZT brane singularities. We see the old blue ZZ brane singularity associated to saddles of the effective potential. We see one FZZT singularity associated to the effective potential evaluated at Z1. And then you see another FZZT brane singularity corresponding to the effective potential evaluated at Z2. So now we have an interplay essentially between three non-perturbative effects. And of course, this picture, I will stop at the two-point function. I don't want to go beyond. The picture generalizes in a very straightforward way to endpoint functions. And again, the Padé approximant analysis completely confirms this picture. Now it's a bit even more involved because we have two kinds of FZZT singularities, the red and the purple. Originally, when they start, both are closer to the origin than the ZZ brane singularities, so the Borel-Padé poles stay attached to them. As I move the red FZZT singularity to the away from the principal sheet of the Borel plane, the singularities of the Borel-Padé attach themselves only to the remaining second FZZT singularity. And then I move also the second one away, and the Borel-Padé singularities attach themselves to the ZZ singularities. Everything that I just said is corroborated also by large order checks. And this also might take a bit to explain, but well, for the free energy, there's no complication. As I said before, and also this was excellently told you by Max, for ZZ brane for free energy, for the free energy, we only have ZZ brane kind of non-perturbative effects, so only eigenvalue tunneling. And how do we generate many free energies to test large genus asymptotics numerically? Well, first of all, the free energies of JT gravity are the VG0 Weil-Petersson volumes. So there is a well-known algorithm by Zograff which allows you to compute many of these Weil-Petersson volumes. By many, I mean order 60. And from them, the trick is to construct sequences which converge to the specific non-perturbative data we want to compute. So for example, this particular sequence here computes for you the instanton action, we have another sequence that computes for you the characteristic exponent beta, and a sequence that computes for you the one loop around one instanton, and so on. The tests that we ran show perfect agreement with what we computed. So our theoretical prediction is the red line for the instanton action here. And well, these sequences of dots are different Richardson transforms of the sequence we are studying. The Richardson transform, I don't want to get into the details of what it is, but it's a way of accelerating convergence. So you see immediately that it converges beautifully to the value we computed analytically for the instanton action. Same goes for the characteristic exponent, which is 5/2 for the free energy of JT gravity. And same goes for the one loop around one instanton, or if you want, for the Stokes coefficient. Now, for one-point functions and in general for correlators, the story becomes more involved because now we have two competing non-perturbative effects, which means that we have essentially two lines in the large genus asymptotics, a blue line corresponding to the ZZ non-perturbative effect and a red line corresponding to the FZZT non-perturbative effect. But now the subtlety is that the instanton action of the FZZT depends on Z. And so as we change the value of Z, the FZZT can become or cease to be the leading responsible for the large genus asymptotics. Unfortunately, in this case, we don't have Zograph's algorithm for computing the WG1. We have to rely on topological recursion, which is quite slow, as I said. We had very few data. I think we had only 7. So we were not expecting to see very good numerics. But instead, surprisingly, the numerics agrees beautifully with the data. So, sorry, the numerics agrees beautifully with the theoretical prediction. So let me explain this plot. Here, the dashed line is the numerical result for the instanton action. As you can see, as we change Z, at first, the numerical result agrees with the instanton action of the FZZT brane, which is this red function here. As soon as the FZZT brane touches the value of the ZZ brane instanton action, the numerics starts agreeing with the ZZ brane, which is essentially the large genus correspondence of the Borel plane singularity plots that I showed you before. Of course, the ZZ brane instanton action does not depend on Z, and so it shows up only as a constant. A very similar story for the characteristic exponent. Here, both are constants, but the numerical result jumps from one constant to the other. So it's 1 for the FZZT and 3/2 for the ZZ brane. One more plot. The one loop around one instanton for the one-point function. Same story. At first, the numerical data agrees with the FZZT, and then it jumps to the ZZ prediction, which are non-trivial functions in principle. So it's really nice to see it happening with so few data. For the two-point function, as I said before, we have even more interplay between non-perturbative effects. We have one ZZ brane and 2 different kind of FZZT branes. So 3 lines of large order contributions. And again, very nice agreement. At first, now we can tune the 2 Z1 and Z2 values. At first, we put ourselves in a situation in which both are smaller than, both FZZT actions are smaller than the ZZ action. And so we only see the interplay between the first and the second FZZT. And then we see the interplay between the first FZZT and the ZZ brane. Same goes for the characteristic exponent, which has to stay constant because the characteristic exponent for FZZT branes is the same, regardless if it's the first one or the second one. But again, it jumps from the first one to the ZZ brane. And similarly, for the one loop around one instanton, interplay between the two different FZZTs and interplay between FZZT and ZZ. Of course, as I said, this story could go on and on with all endpoint correlators, but it generalizes in a very trivial way. Now, finally, resummations, because now, okay, I've given you a recipe for computing non-perturbative data using topological recursion. And in fact, it's a recipe that is not restricted to this class of models we are considering. It's a recipe that applies to any matrix model, essentially. But of course, our motivation originally was to study non-perturbative effects in two-dimensional gravitational theories and for a specific class of observables. So now we want to see what kind of effect these non-perturbative effects have on a certain kind of observables. And first of all, I would like to study the spectral density. Now, in the airy toy model that I told you before has this very simple spectral curve from which there results a very simple spectral density of eigenvalues. We have an exact formula for the full non-perturbative spectral density, because of course, this ρ0 of lambda is just the perturbative contribution to the spectral density. In reality, eigenvalues, because of effects like eigenvalue tunneling, will distribute themselves on a larger support than what the perturbative spectral density tells you. And the airy toy model, I call it a toy model because we have extreme control over it, so we can compute essentially everything exactly. And in particular, the non-perturbative spectral density can be computed in terms of the airy function. And as you can see here, I plotted the perturbative in blue and the exact in orange. And you see immediately that in the perturbative case, we had our eigenvalues that were distributing themselves only on the cut, so going from 0 to -infinity. But the exact function gives us a correction to this picture, which involves eigenvalues that distribute themselves also in what is called the forbidden region. Of course, with an exponentially damped behavior, but still they are there. And also the non-perturbative effects, on top of adding some eigenvalues in the forbidden region, they also added some wiggles in the allowed region, which is an effect that is well understood when one looks at for example, at the interplay between FZZT actions. Now, does this picture keep working also in JT gravity, for example, which is an example on which we have much less control? And it does. So when we add FZZT contributions to the perturbative JT gravity spectral density, we see exactly the same effect. But this, word of caution, this plot looks much uglier, but it's uglier in a way we can control, in the sense that these divergences you see at the origin, both in the forbidden region and in the allowed region, these are well understood by the fact that we are essentially doing an asymptotic expansion in a region that does not agree well with the expansion at the origin. But still, if we forget about these divergences that we know what they are caused by, we get exactly the same effect that we are expecting. So wiggles in the allowed region and exponentially damped presence of eigenvalues in the forbidden region. Another story that is interesting is the story of the spectral form factor. I told you before that this is an observable we are very interested in because it tells us about black holes and quantum chaos. Actually, the story is a bit less clear than, for example, in the spectral density, because a very recent result showed that the spectral form factor is actually given by a convergent power series, because there are some, by the way it's defined, and because of properties of intersection numbers and Weil-Petersson volumes, there are some miraculous cancellations which turn this the defining power series that constructs the spectral form factor into a convergent one. However, and this can be seen in another way, by taking, for example, the FZZT contribution to the two-point correlator and perform the Laplace transform that takes us to the spectral form factor, you realize immediately that the FZZT contribution, from being a non-perturbative contribution, turns into something that can be perturbatively captured by a Taylor expansion. So we can still, in principle, take the FZZT contribution to the two-point correlator, Laplace transform it, and see if it reproduces the plateau which was appearing in the spectral form factor. And this we did in the Airy case, but we probably will be able soon to generalize it to the JT gravity case. And we see indeed that by adding this FZZT, this Laplace transformed FZZT contribution to the spectral form factor, we obtain exactly the plateau that the pure perturbative was missing. But this is a subtle way of adding non-perturbative effects, because, as I said, the object is captured by a convergent series. Now, I've told you pretty much everything I wanted. I just want to summarize what I told you and give you some ideas for future research. So, using topological recursion, we have a very systematic way of computing non-perturbative effects in 2D gravitational theories, and in fact, in a much larger class of models. And this extends to free energies and correlators, which is, I think, the most non-trivial part of this construction. We checked and verified that there is a competition between FZZT effects and ZZ brane effects in the Borel plane, and this translates to a competition in the large genus asymptotics of the objects we are considering. I didn't show you explicitly, but this indirectly gives us a way of writing down large genus, very precise large genus asymptotics for Weil-Petersson volumes in a very easy way. And also by some addition of FZZT brane contributions, we were able to reproduce the plateau region of the spectral form factor in quite a simple way. Now, there are a lot of ways in which these kind of techniques can be generalized. Well, first of all, we stuck only to one instanton contributions. And we would like to include them, and probably the hardest task would be to be able to write down the full resonant transseries for JT gravity. Because as I told you, on top of being a matrix model in which we know that resonance is at play, we have this weird structure of saddles in which all instanton actions are multiples of each other with alternating signs. So we expect a very non-trivial structure there. And also, a question that I really care about is, how do we extend these techniques to spectral curves which do not have an underlying matrix model? Because, of course, in principle, if I give you a spectral curve, you don't have a matrix model description for it. And therefore, you don't have an eigenvalue integral that you can associate to it. But our technique relies a lot on performing this eigenvalue integral on a contour that passes from the non-trivial saddle. So how do we generalize this? There are some hints that this can be done without relying on eigenvalue integrations, but still this should be very precise. So this is it. Thank you very much for listening.
Definitely times for questions, comments.
Could you go to the plot of the Borel plane with Hadé poles in?
Yeah.
Maybe the first one.
Oh, yeah, this is the first one.
So just to make sure I understand correctly. So here the blue singularity is in the principal sheet.
Yeah, exactly. And it stays there because it doesn't move.
And the fact that you don't see any poles coming out of it is simply because you don't have enough perturbative
Yeah, exactly.
data.
So the thing is, we could generate very few perturbative data. So the Padé singularities only condense close to the closest singularity to the origin. If we had more, we would have seen also a little bit of condensation close to the ZZ brane singularity. Yeah.
Okay, thank you.
Just before any other question, just wanted to ask also on this: do the singularities coalesce, the ZZ and the FZZT, or do they just change dominance?
So they change dominance. Of course, one can tune things in such a way that they sit at the same spot, but
Not the general case.
But not the general case. Yeah.
Questions? Any other questions? Comments?
So there you have like a Borel plane with the singularities depending on Z.
Yeah.
Is it the case that this correlator, or whatever it was, solves some like singly perturbed differential equation? Or
Okay, so yeah, the story for JT gravity is quite complicated because in principle, these correlators, well, in general, to a spectral curve, you can associate a quantum curve, which will be solved by some wave function, which is more or less the object. Well, you probably recognized it, this object here. This typically solves some quantum curve. And then from this object, you can construct, using the so-called determinantal formula, you can construct the WNs. So for example, you can construct W1 is some quadratic function of this wave function. And in general, also W1 will solve some differential equation. So yeah, in principle, this guy here, you can construct it through WKB, and this is essentially what it is. I mean, the usual lore in which topological recursion reconstructs WKB for you, in some sense.
Do you expect that there could be a beta deformed analog of all this?
Sorry?
Beta deformation.
What would it be?
I'm wondering, like, if it, or you mean, okay, I mean, beta deformed matrix model is somewhat random deformation. Like, can you generalize that to it?
Okay, no, okay, I see what you mean. We haven't thought about it yet, but yeah, it's been in the talks, but yeah, we haven't really sat down.
Any other last question?
Apologize, I came in late, maybe already said it. What are the instantons in JT model?
What are the instantons? So as I said, there are two classes of non-perturbative effects. You have ZZ branes, which are just standard eigenvalue tunneling when you look at the matrix model picture. And then you have FZZT branes, which only will start appearing in correlators and not in the free energy. And those are essentially associated to this determinant insertions. So they are associated to this wave function, and you can see them. Seeing them as determinant insertions is a bit misleading because you might think that you have to insert artificially an operator to see this kind of non-perturbative effect. But in fact, as I was saying, the WNs can actually be constructed in terms of this wave function using this Okunkov determinantal formula. And if you do that, you see immediately that this kind of contribution needs to be there also in correlators.
Yeah, thank you.
Okay, then let's thank Paolo again. And we'll see everyone again tomorrow at 9. Thank you.